Hello, welcome to a video on section 7.3, part 2, regarding volumes of revolution. So what is volumes of revolution all about? So what we're going to do is we're going to take the curve and rotate it about a line. That's essentially what we're going to do. So we rotate a region about a line. Say, for example, we have y equals root x, which I know looks like that. But what if I focus on from 0 to 1? And I have this region right over here. If I rotate that about the x-axis, you're going to form this solid, which looks like this over here. Kind of looks like a dome a little bit. Now, what we're going to want to do is find a cross-section or get a cross-section and figure out what shape it is and find the area. So this right here that I just circled is the shape of a cylinder. So total cross-section is a cylinder, or you could say it's a disc, with a radius of root x. That's because this distance right here, oops, not sure what happened there. This distance right here is determined by the vertical distance from the endpoint on root x and the x-axis. So you can think of this as being x comma 0, and that point as x comma root x. So our radius is y upper minus y lower. Y upper minus y lower. Sorry, it's messy handwriting. So radius of root x, our area of course is pi root x squared, which of course is pi x. So the volume of the solid will be from 0 to 1 of my area times dx. And the volume of approximating a cylinder is usually, as we know, pi r squared h. So in these cross sections, of course, we're perpendicular to the axis of rotation, so the center of the disk will lie on the axis of rotation. Let's take a look at another example, then I'll run a simulation. So say, for example, we have this curve, which actually I think this is going to be semicircular. Yep, that is definitely a semicircle. Now, if it rotates about the x-axis, again, typical cross-section, again, it's going to be a disk. In this case, our radius is going to be root a squared minus x squared. And the area is going to be pi times the square of all that. So the volume of the solid. Now we have to find out where our bounds are going to be. When y is 0, we have that. So x is going to be plus or minus a to make that 0. So we're going from negative a to a of pi a squared minus x squared times dx. So it's kind of an extension of what we did in 7.3 part 1. Now let me run a simulation here so you can kind of get a better idea of what we're trying to do. And hopefully it turns out pretty well. So here's y equals root x. That's being drawn. And y equals 1/10 x. Now this is going to be a little different because we were rotating about, well actually we were bounded by the x-axis. This is bounded by x equals 4. If you're going to take that region and rotate about the x-axis to form a solid. So you can see how it kind of forms something that's kind of like a dome, but there's a hole in the middle. Now, this process we're going to see in 7.3 part 3, which is called a washer method. But it's going to be a little bit, what we're doing is obviously not going to be hollow, it's going to be solid. Because our region is actually bounded by the x-axis, not by, in this case, y equals 1/10 x. So that's kind of what we're trying to get at with this stuff here. Let's do a couple more examples, wrap up the video. So say, for example, the region between the graph f of x is 2 plus x cos x and the x-axis interval -2 to 2 is revolved about the x-axis which generates a solid. Okay, so here's -2, here's 2. So it's almost like we're forming a little vase in a way. So it's kind of like that. Our cross-section using half thickness of delta x. The volume of the solid is simply going to be from -2 to 2. And our radius is just really what we see for y here. So it's going to be pi 2 plus x cos x squared times dx. So we can kind of generalize that our volume is simply going to be from a to b pi, whatever f of x is, squared times dx. And last one, y equals x cubed, which looks like this, and y equals 8, horizontal line, and bounded by the y-axis. Now, yeah, because that's x equals 0, and we're going to rotate about the y-axis. So it's going to actually look like that. That's how the solid's going to look. So we sketch our graphs. Actually, I kind of reversed. I did this graph of the region, the big axes, the volume of revolutions, large axes. But essentially, we're just going to be rotating about the y-axis, this region here. Typical cross-section actually now will be delta y, because our disks are going to be stacked horizontally on top of each other. So we're entering from bottom to top and top to bottom. So we're summing a bunch of horizontal cylinders of thickness delta y. So we need a function, our area's got to be a function of y. So in this case, that's x right, and that's x left. So our radius is x right minus x left. Or x right we could think of as being x comma x cubed. Or sorry, let me take that back. X cubed comma, we want this in terms of y. Hold on, why am I confusing myself? Okay, the y values are the same. No wonder I'm confused. I gotta get x in terms of y. Cube root of y, there we go. So x right's cube root of y, comma y, and the x left is just going to be x is 0, of course, and y is y. So our radius is just going to be cube root of y minus 0, and I'm integrating from 0 to 8. That's going to be my boundaries because I'm doing this differently now. I'm doing this in terms of y. And pi, my radius, times dy. You can work it out, but I think you kind of get the idea. So if you're doing this volume in terms of y, then you just go from c to d. So here's c, here's d, pi f of y squared times dy. And that's that. Okay, looks like we're all set.